Okay, class, good afternoon. So for today, let's have now our last topic, which is the footings. So footings are reinforced concrete foundations utilized to support columns and walls. Usually, they support your columns. Okay, and then you have four types of footing. You have first is the wall footing. You have here the wall, and then you have your footing, okay, with the corresponding bars. You have the temperature bar for the footing and also for the main bar. So this is continuous up to you have walls in your uh, foundation. Next, you have the spread or isolated footing. Okay, spread or isolated footing. So usually you have there your column at the center, and then in some cases you have the this foundation. You have your column at the side or at the corner of the footing. So that is also called spread footing or isolated footing. Sometimes that is square, or you can have rectangular footing. Okay, but in your column you can have a square, rectangle, or circular columns. Okay, next is combined footing. So you combine the two columns. So in this case, you can have this scenario if ever you have a smaller distance in between your columns. So you can have the combined footing. Okay, and then you have the rough foundation, or sometimes that is called mat foundation. Okay, so that is mat foundation. You have the foundation of all your columns. Okay, so in some cases when you excavate the area, sometimes you also have the this one connecting maybe from column to column or footing to footing, especially when you are using spread footing. Okay, sometimes that connects the footing or column. So for example, this is your footing and another footing and column. You have there the connection. This is the tie beam. This is also part in your foundation, but this is not part in your footing. Sometimes the footing is connected to the tie beam, so that the if this area will settle, so it is connected to this footing or this foundation. So the settlement of this area is equal or level. Or sometimes if this soil is loose, so maybe it's a hanging, since you have the soil portion here, so you have the settlement. Okay, so that is the types of foundation or footings. Next is the distribution of loads to soil. Okay, you have the distribution. Usually the excavation of the foundation or footing, normally from 1 to 2 meters, but in the code that is h/2. So imagine if you have a 6-story or 6 meters height of building, you need to have 3 meters excavation if you are to follow the code that is h over 2. But in our case, we only have 1 to 2 meters excavation depth. Okay, so you have first case 1, you have uniform distribution of soil load. So your eccentricity is equal to 0. And then you have your Q, that is the actual soil pressure, is equivalent to P. Your P is the load carried by your column to the footing. And then you have B and L, that is the dimension of your footing. Okay. And then for case 2, you have an increasing load. So unlike this one, you have an equal actual soil pressure. For this one, you have different actual pressure. You have the minimum and then the maximum. So this is now case 2. So your eccentricity is less than your L over 6L is your dimension. Okay, so entire footing subject to soil pressure. So your formula now for determining the Q, that is the actual soil pressure, you have the formula P, your load in the column, divided by the area. Area is the width and length of your footing or foundation. Then plus minus, you have MC over I. You have the moment here since you have the eccentricity with this distance. Okay, and then C now is your L over 2. This is the center line. So your C is from the neutral axis to the outermost fiber, so L over 2. Okay, and then you have a rectangular or square section. You have the I equivalent to BH cube over 12, or that is BL cube over 12. Okay, so therefore you have your Q is equal to P over BL plus or minus. Plus or minus meaning plus, that is maximum, minus, that is minimum. Okay, so you have 6P times E, that is the eccentricity, where the eccentricity is equal to the moment divided by the force P of your column. So therefore your Q max is equal to P over BL times 1 plus 6E, that is the eccentricity, divided by L. So that is the formula in solving the actual soil pressure. By the way, for the QUA, that is the soil bearing capacity. Okay, so for case 3, you have your eccentricity is greater than your L over 6. So the portion of the footing is not subjected to soil pressure. So you have this one. So some portion of the footing is not subjected to soil pressure. Okay, so your formula, you have your R is equal to Q max divided by 2 times 3A times B, where your A is this one. So that is A is equal to 1/3, and this one is 2/3. Okay, since this is a triangle, you have the centroid, so this is 1/3, this is 2/3. Okay, so the formula now for the Q max, that is equivalent to 2 times R, where your R is equivalent to your P, and then 3 divided by 3 A times B. So therefore your Q max is equal to 4P over 3B times L minus 2E, where your Q min, or the actual soil pressure, is minimum is equal to 0. So in this type of cases, okay, you need to check if your eccentricity is greater than or less than L over 6. Okay, so let's have the last problem or sample problem. So you are to design a spread footing for a column of 500 by 500 millimeter in section to carry a dead load of 1000 and a live load of 1500. You have the allowable soil pressure, you have the QUA equivalent to 150. You neglect the weight of the soil above. So if you are given the unit weight of soil, for example 18 kilonewton per cubic meter. So if in the problem you are to solve for the soil weight, so you need the depth and then the size of the footing. So you compute the volume of soil above your foundation. So that is the weight of the soil above. And then you will use FC prime equal to 21 megapascal, Fy is 414 megapascal, and your modular ratio N is equal to 9. Okay, usually when we design the weight of the footing, it should be 10% of the column load, since usually for the 10% that is much higher when you compute the load of your footing. Okay, 10% of the load of your column. Okay, so usually this is the percentage used to assume the weight of your footing. Okay, to solve for the actual P, so actual P here, you have P of dead load plus P of live load, which is 1000 plus 1500, so that is 2500 kilonewton. Okay, and then the weight of the footing, so that is 10%. So this weight, that is 10% of the load of the column, so that is 250. So therefore the total weight or the total load, that is 2750 kilonewton. Okay, so next is to compute the area required of your footing. Okay, so to compute for that, you have the formula WT divided by the allowable soil pressure, or the soil bearing capacity. Okay, sometimes this is called the soil bearing capacity. Okay, so therefore you have this formula WT, or the total weight of the footing carry divided by the soil bearing capacity. So you have 2750 divided by the allowable soil pressure, which is 150. So you have your area equivalent to 18.33, where your area of your footing is square, so that is P. So therefore the area is equivalent to L times B, where this is a square footing. So therefore your L is equal to B. Okay, so therefore you have your area equal to L squared. So you have your area equal to L squared. To solve for L, since this is a square foundation, so you have the square root of 18.33 square root of 18.33. Okay, so you now have your L equivalent to 4.28. So normally when we try our footing dimension, you have to round it up to 0.1 usually. Round it up to 0.1. So since this is 4.28, so therefore that is 4.3. Round it up to 0.1 meter. So any value, you round it up to 0.1 normally. Okay, so when you try, so since this is design, so you need to try the dimensions. If this dimension, you have to check for the bearing, punching shear, the bending. So if this trial will fail, so you need to have another trial. So next to this dimension is 4.4. Okay, so to check, you have to try this dimension. So you try 4.3 by 4.3. So you solve again the area using 4.3 by 4.3. So you have 18.49. And then your P load just for the column, you have 1,000. This one is 1,000. This one is 1,500. So you have P equivalent to 250, 2,500 kilonewton. So to check if your actual soil bearing capacity or actual soil pressure is less than your allowable. So let's check. You have the formula Q, or the actual soil pressure, is equal to P divided by the area, where your P is this one, 25, divided by the area, which is 18.49. So your Q now is 135.21, and that is less than 150. Therefore, safe. Since this is your actual, using this area, and then this is your allowable. Okay, it should be that your actual is less than the allowable to be safe. If this is greater than the allowable, therefore fail. So you need to try another footing dimension. Okay, so when you have this equation safe, you proceed with the checking of punching shear, or you solve for the depth of your footing. Okay, so you have this footing, you solve for D. Okay, this is the cover. You solve for your D. Okay, so you now have the dimension, which is 4.3, and then the punching area, that is the distance from the outermost of your column to D over 2. So that is the area of the punching. So when you have this load, when you have a load here, maybe in this point your column is heavier, so, and then you have your footing which is not too depth, you have the smaller dimension for D, so maybe it breaks, so you have the punching shear. Okay, So the distance of punching area, you have D divided by 2, same as with the other side, where your C is the column dimension, which is 0.5. So therefore you have the formula for the allowable punching shear. You have the allowable punching shear BCP is equal to 0.17 times the square root of FC prime. So therefore you have your BCP equal to 0.78 megapascal. And then the actual punching shear, you have BP. The formula is V over AP, where your V is equal to Q, that is the actual Q. So the actual Q is your P divided by the area, which is 2,500 divided by the area, that is 18.49. So therefore your Q is 135.21. Okay. And then you have your L, that is 4.3 minus C plus D. Your C here is 0.5, that is given in the problem, and D is the unknown. And then for AP, that is the punching shear area. So this one, that is the punching shear area. So you have C plus D. Okay. So since this is D over 2 and D over 2, so therefore this is equal to D. Okay. So that is C plus D, and then plus D, that is the height, times 4. Okay, that is 4 sides. So that is 0.5 plus D. 0.5 here is the column dimension, and then multiplied by D times 4. So you equate your allowable equivalent to your actual to be safe. So therefore your actual is 0.78 megapascal. So you substitute the values. You have now your formula BP, which is equivalent to BCP. Okay. So you have your V is equivalent to VP times EP. Okay. So you substitute the values. So once you have substituted the values, you can solve this using shift solve in the calculator. So the answer is 0.648, or you can use the quadratic equation, the same answer, that is 0.648, and then you round it off or round it up to a multiple of 10 mm. So therefore you will use your D equivalent to 650. Okay. So next is you design for bending. Okay. So for the design for bending, you have this, the critical section for bending is this one. So right after, or the face of your column, that is the distance or the area for the critical section for bending. Okay, so you solve for that distance. So solving for this distance, that is, you have your length, which is 4.3, and then you divide it to solve for this distance, that is 4.3, you divide it by 2, minus the column, that is 0.5, you divide it by 2, so therefore that is 1.9. So this is the distance. Okay, and then you have the assumed D, that is 0.65, and then your soil pressure is 135.21. So you will solve for the moment. Okay, so this moment, you have the moment here. Okay, so this is the area, so you have the moment. So to solve for the moment, you have the soil pressure, that is 135.21, multiplied by 1.9, and then multiplied by 4.3, and then you multiplied it by 1.9 divided by 2. So therefore, you have your moment equivalent to 1049.43. And then you recompute your D to check if you have a safe in bending. So to recompute your D, you solve it using this formula, the resisting moment of concrete, that is MC 1/2 FC kg BD squared. So as what I have said, I will not use this formula, since when you are using this formula, your R here is already rounded off. So unlike for this one, when you use this, so no values are already in or no values are rounded off. Okay, so we will use this formula. Okay, so given you have FC prime, so you solve for FC, and then Fy is also given, so you solve for Fs. So now your Fc is equivalent to 9.45, your Fs is 207. So you substitute, or okay, solve first, by the way, your K and G. So the formula for K, you have 1/1 plus Fs and Fc, or that is equivalent to N over N plus Fs over Fc. Okay, or I think so, it's maybe in reverse, Fc over Fs. Okay, so it depends on your formula, but the answer is still the same. Okay, so for K, you have your value for K, that is 0.291, and then for J, that is 0.903. So substitute all the values, this one to this one, so you have your D equivalent to 463. So therefore, since this is dimension, you will use the bigger dimension for this D. So therefore, use your D from punching shear. So we already solved D for punching shear, which is 650. So we will use 650. Whichever is the higher, if the recomputed D for the bending is much greater than the punching shear, so maybe we will use that one, if that is bigger or higher than your D from punching shear. Okay, so but since we have a higher D from punching shear, so we will use this D, which is 650. And then next is the steel reinforcement. So for steel reinforcement, you have the formula for the resisting moment of steel, which is the area of steel times the Fs times GD. So you solve for the area of steel, you have your Ms, should be equal to your moment, which is 1049.43. Okay, and then you have your Fs, which is 207. Then J is 0.903, and your D, you will use the D from the punching shear, not from your resisting moment of concrete in your bending design. So if the reverse is not given, maybe you will use 25, but the standard or the minimum bar diameter used for footing is 12 mm. Okay, if that is not given the problem, you can use 12 up to 32 or 40 millimeter. So it's up to you. what diameter you used in your design. But normally you have to be uh, you have to design it with common sense, since if you use 12 mm, maybe the bar diameter is so many number of bars. So if you have the bigger bar, so that is less number of bars. So it's up to you how you design or how you pick your bar diameter in your footing. Okay, it should also be balanced. If you have 2 by 2, so maybe you can use 16, so that maybe that is up to 10 reinforcement. If you will use 12 mm, maybe it's up to 20 number of bars. It's up to you how you design. If the steel reinforcement or the bar diameter is not given in the problem, so in this case you will use the 25 mm bars. So you have now the number of bars equal to 18, or that is 17.6. But for number of bars, it should always round up, always round up to whole number. Okay, so therefore you will use 18 25 mm bars both ways, since this is a square footing. Next is to check for your beam shear. So you have also a critical section for beam shear. To solve for that, that is the distance from the outermost fiber of your column to this one is D. So therefore, this distance minus D, that is your critical section for the beam shear. Okay, so to solve for that, you have this distance, which is 1.9, that is from the bending, and this is 0.6, so therefore 0.65 for D, so therefore 1.9 minus 0.65 is equal to 1.25. Okay, so to solve for V, okay, to solve for V, you have this, the actual soil pressure multiplied by 1.25, this distance, multiplied by 4.3. So you have your V equal to 726.75. So the formula for allowable shear stress, you have the 0.09 FC prime. So therefore, your allowable shear stress is 0.412. And then for the actual shear stress VP, so formula is equal to V, this one, over BD. Okay, B is the length or the base of your foundation or footing, which is 4.3, and then D is the depth of your footing, which is 0.65. So therefore, you have your actual shear stress equivalent to 0.26 megapascal, and that is less than the allowable, so therefore safe. If the actual is less than the allowable, it should always be safe. Next is the band stress. Okay, so checking for band stress, you have also the critical section for band stress or band, so which is equal to the bending critical section, which is 1.9. So you solve for the band stress, which is allowable bond stress, which is 10.14 times the square root of FC prime divided by the diameter you used in this foundation or footing. Okay, but before that, we will solve for V, which is 135, that is the soil pressure, multiplied by 1.9 times 4.3. So you have your V equal to 1105. And then you solve for the allowable bond stress. You have this formula. FC prime is 21, and then the diameter of bar you use in your footing. So therefore, your allowable bond stress, that is 1.859 megapascal. So to solve for the actual bond stress, this is just the same with the beam formula. That is, the actual bond stress on mu is equal to the V. You have this V divided by summation of O times JD, where your summation of O is the summation of pi times the bar diameter. So summation, you have the number of bars multiplied by pi multiplied by the diameter of bar used in your footing. So the summation of O, you have 1414 millimeter. So substitute the values. You have V, which is this one, 1105 divided by 1.414. J is 0.903, and then D is 0.65. So you have your actual bond stress, that is 1.331, and that is less than the allowable, which is 1.859. So therefore, safe. Okay, and then next, you check for the weight of the footing, since from the beginning you have the assumed 10% of the column load. So at this portion, we will check for the weight of the actual footing, or actual weight of the footing. So the formula of the weight of the footing, you have the weight of concrete, which is 23.54, then the L and the B, or L, multiplied by the thickness of your footing. Okay, so the thickness is equivalent to D plus the 1.5 of the bar diameter, since your D is from the top up to the center of the bar diameter used, and then your cover is from the bottom up to the main reinforcement. Okay, so you have your thickness is equivalent to D plus 1.5 or the bar diameter used plus 75. So therefore, you have your D equal to 650, and then you have your diameter used, that is 25, so multiplied by 1.5, plus the cover. Normally the cover of the foundation of footing is 75 mm. So you have a total thickness of 762.5. Say, maybe you round it off to a multiple of 10 up. Okay, round up to multiple of 10 mm. Okay, so let's say you have your thickness equivalent to 770. Okay, so solve for the weight of the foundation, which is 23.54 times 4.3 times 4.3, and then the thickness is 0.77. So therefore, you have your actual weight of your footing, which is 335. Okay, so you compute now your actual soil pressure. So you have the load from the column, that is PDL plus PLL. So So that is 1,000 plus 1,500. So therefore you have 2,500, and then plus the weight of your footing divided by the area of your footing. So that is equivalent to 153. So since you have a difference of 3 kilopascal, maybe you have to say that that is equal to 150. Okay, since that is a small difference between the two. Okay, so maybe you round it off to 150. Since you have your soil bearing capacity or the allowable soil pressure of 150. If you are not satisfied with this calculation, maybe you try to change your area. So you try 4.4 meters for your length or sides or dimension of your footing, so that you come up with the soil pressure less than your allowable. Okay, so no need to revise the size if okay. If not, you revise the size. And then last is the reinforcement detail. So normally when you design the foundation or any other structural members, it should have the reinforcement detail. So that is part in the structural plan in your drawings. Okay, so you have now your thickness, which is 770, and then the bar used. So this is the section, this is section, this is plan. Okay, so the bar diameter used and the number of bars showing the section, then the thickness, and then in the plan view you have the dimension of your footing and then the bar used. Okay, so that's it for the design of footing or foundation. Thank you. If you have question, message me in our